Hello, everybody, and welcome to the Astro Show, the place to be if you're curious about the cosmos. I'm your host, Dr. Sam, the founder and executive director of Wyoming Stargazing. Here, you can pick the brains of astrophysicists, get advice from an aerospace doctor, find out what scientists have to say about life, and learn about what's going on up above your head, all in the same place. So we hope you join us every second and fourth Tuesday of the month. This month, the third and the fifth Tuesdays at 6 p.m. Mountain Time on Twitch, YouTube, and Facebook as well. In this week's show, we have Dr. Jan Eldridge, astronomy professor and head of the physics department of the University of New Zealand in Auckland. Among other things, Dr. Eldridge studies the evolution of stars with the help of a computer program called BPAS that she wrote. We will hear all about that from Dr. Eldridge later this evening, but before that happens, let's welcome our co-stars. First, astronomer and data visualization engineer at the Adler Planetarium, it's Dr. Lauren Corleys.
Hi, everyone.
Hey, Lauren, good to have you. Next, aerospace doctor and founder of Orbital Biodesign, it's Dr. Danny Carroll.
Hi, everyone. Good to see you.
Danny, good to see you as well. Next, astronomer and host of her own YouTube show, Nora's Guide to the Galaxy, it's Dr. Nora Bailey.
Hey, everyone.
Hey, Nora. Next, author and founder of the Space Tourism Guide, it's Valerie Stymick.
Hi, everyone. Great to be back.
Good to see you, Valerie. And our special guest for this evening, straight from Auckland, New Zealand, Dr. Jan Eldridge.
Kia ora, everyone.
Hello to you as well. Thanks for being here. All right, well, let's get started. As always, we will begin with a welcome to Dr. Jan Eldridge. Thanks so much for being here. And now we will move into astro advice. So I'll read the quotation for this week, and then the co-stars and our special guest will have a moment to consider which of the four possible quotators actually said this, and then we'll chat about it. So here you go. Science makes people reach selflessly for truth and objectively. And objectivity. It teaches people to accept reality with wonder and admiration, not to mention the deep awe and joy that the natural order of things brings to the true scientist. So that is the quotation. First possibility is Émile de Châtelet, who was a French natural philosopher and mathematician from the early 1730s. She was responsible, among other things, for doing what was still considered to be the standard French translation of Newton's Principia. Option B, Rita Levi, Italian Nobel laureate, honored for her work in neurobiology. She was awarded the 1986 Nobel Prize in Physiology or Medicine, jointly with her colleague Stanley Cohen, for their discovery of the nerve growth factor. Option C, Stephanie Kwolek, who was a Polish-American chemist who's known for inventing Kevlar and worked for DuPont for more than 40 years. And option B, Lise Meitner, who was an American-Swedish physicist who was one of those responsible for the discovery of the element protactinium in nuclear fission. But unfortunately, in the all too common story, she was not awarded the Nobel Prize for that discovery, although her male colleague, Otto Hahn, was. So those are your four options: Émile de Châtelet, Rita Levi, Stephanie Kwolek, or Lise Meitner. What do y'all think?
I'm going to pick A because this feels like a mathematician to me.
Okay. So Dr. Lauren votes for Emily A. Châtelet. Who's next?
I have no idea, so I'm just going to go with D for fun.
Okay, one vote for D from Dr. Nora.
I'm going to say C.
Was that Danny? All right.
Yep.
Dr. Danny goes for C, Stephanie Kwolek. Valerie, Jan?
Well, I'd go for Liza Meitner, a D, just because, while it sounds like a mathematician, it also sounds a bit like a physicist, especially if you're kind of thinking about, because, what she did with the radioactivity was a really difficult problem. So it kind of, they had to really change people's conception of reality in some ways. So I'll go D.
Oh,
I have no idea otherwise.
All right.
Okay, well, that worked out well because I was going to go with B, Rita Levy, only because I think you said she was in some like neurophysiology or neurobiology. Yeah. So that sort of feels like what this ties into. So now we have it across all the answers.
Fair enough. I love it when that happens. Thank you for humoring me if that was what you were doing.
No, that's already what I was thinking.
The correct answer was D. So we got a point for Jan and a point for, was it Lauren?
No.
That's me.
Nora. Point for Nora.
Totally unearned.
Well, sometimes luck is all you need. What we've heard a little bit about what you think about this. What are your other thoughts?
Well, it's a really good quote because basically all we do in science is, it's really difficult to have that objectivity, not to trust your gut instinct and ignore it. But sometimes you have to, because, you have to confront when you do get things wrong and they don't work the way you want to. But it is that true joy that, you learn something new. That's just so cool. That's why we all do this, right?
Indeed.
I also like that she's responsible for the discovery of something entirely new, a new element. And the sort of the part that's jumping out from the quote to me is science teaches people to accept reality, because the element already existed, it just hadn't been discovered. So science continues to progress by pushing us to accept what's already reality that we just didn't know or understand yet.
I like it. Nice.
I really
like
liked the end of this quote, saying that, kind of understanding things via science brings this deep awe and joy. And I really like that because I know sometimes I hear people say things like a sentiment of like, oh, doesn't it ruin the mystery a little bit to like be digging into these things and like, why don't just accept like the way they are? But to me, it doesn't. To me, it does bring more awe and joy to understand it more deeply and more fully. And I don't feel like there's a loss in digging for that knowledge of why and how things are the way they are. So I like that.
Yeah, I agree with you, Nora. I remember hearing a interview with Richard Feynman, and he was asked a similar question about how his exploration into the quantum realm either detracted or accentuated the beauty that he found in the natural world. And he was arguing that it just accentuated it for him. The more he knew, the more beautiful everything became. Any other thoughts? All righty. Well, let's move along then. Astro 365, this day in astrophysics history. On this day in 1971, the Mars space probe Mariner 9 left Cape Canaveral and made it to Mars thereafter on the 13th, which was the first artificial satellite in Martian orbit. And there are lots and lots of those now and lots of Mars landers, but yeah, this was the first. And it's hard to believe that was just over 50 years ago. Time flies.
But it's after we landed someone on the moon. I learned this fact recently, and that blew me away. People travel so much harder than sending these sorts of artificial satellites, but we decided that that was what we were going to do first, and that just, I don't know. I was surprised by that fact.
Yeah, and I mean, I think that was, it was just based on the space race, right? It was because we needed to be first before Russia, and I wonder if the Cold War hadn't have happened, if we would have made it to the moon as quickly as we did, or whether we would have been landing probes on Mars and other planets long before we actually made it to the moon.
Maybe. It just feels like it was ill-considered. Like, maybe we should send more robots before we send people. But we're like, no, let's just put people already.
I think there were
hindsight, it's freaky.
There were. I think the Russians tested a few animals, right? They had a couple space dogs. And I think was there a turtle as well? I think there was this. I think the Russians sent a turtle first. There were a couple other animals as well.
But I think, wasn't it, if you look back at some of the early space probes, they were really pushing the technology they had. So to actually get any space probe, robotic space probe, that far was actually, sounds stupid, much more difficult than landing a person on the moon, because you've actually got a brain there that can adapt and change and deal with situations. But, it's kind of difficult, so difficult now to place yourself back that time and realize how bad the technology was in comparison. And it's actually amazing because I think, the Voyager space probes were launched 6 years after this.
Yeah.
So to go from just doing that first one to doing a mission that's still running today, it is kind of crazy. And I think this may also be the one mission, if I remember correctly, that got to Mars and there was a dust storm. And so they was all disappointed. But then slowly as the dust storm receded, that's when they started seeing Olympus Mons revealed. And it was kind of like, must have been a really weird thing to actually get there, be disappointed, and then suddenly over time, waiting to see Mars be revealed as the dust storm subsided.
Oh, nice. I didn't know that. That's a great story. Kind of like, not quite as dramatic, but almost as dramatic as getting the corrective lens on the Hubble Space Telescope.
Well, to be fair, this one worked. It just was Mars was not cooperating. Its technology was
problem. Yeah, should have been less predictable.
This one's just solved with time.
Yeah. Dr. Nick, hello.
Hello there.
Good to see you again. Welcome back to the States. When did you get back?
I've been back for a bit, but about to head out again in a few weeks.
Okay.
Bouncing back and forth.
Yeah, well, we'll have to hear all about how Chile was at some point. All right, well, it is time for everybody's favorite part of the Astro Show now, the astronomy news quiz. So as a reminder, it's all lightning round. And so you just have to answer the questions as fast as you can in order to get a point. So far, we've got, we've got our special guest Jan with 1 point and Nora with 1 point. All right, here we go. Question 1. What sadly will likely be invisible to the unaided eye in roughly 20 years?
Venus?
It's even more dramatic than Venus. Venus might actually still be
Polaris?
visible. It's bright enough. Polaris is definitely going to be gone in 20 years, the unaided eye. Yeah, this is really scary. Yeah.
The moon?
Fortunately, the moon will still be visible. That is right. But I like where you're going, Danny.
Do you mean like it's going to not be visible intrinsically or just because of light pollution?
Because of light pollution, yeah.
I was like, why is Polaris not going to be visible in 20
Not
years?
to the unaided eye. Yeah.
It isn't going anywhere.
Maybe the
Yeah,
ISS?
The ISS
Milky Way.
will probably still be visible. The Milky Way is going to be long gone before then. We're talking about most of the major constellations. If the light pollution continues to increase at the rate that it is increasing now, in 20 years, most of the major constellations will be invisible to almost everyone on the planet.
Wow.
Yeah. It is scary. So folks, turn your lights off at night. Don't do that. All right, next question. A weird line of stars previously thought to have formed in the wake of a supermassive black hole escaping its host galaxy might actually instead just be what?
An edge-on galaxy.
An edge-on galaxy. That's a point for Nora. Yeah, it was big talk about this stream of stars being created by an escaping black hole. New analysis suggests that it's probably just an edge-on galaxy. And there are lots and lots of those.
I feel like this is the first time we've had one where it's like, it's a less dramatic discovery. It's almost always like a mind-blowing discovery of some new galaxy or black hole formation. Nope, this is actually nice and calm. Okay, that makes sense.
This was not one of those. This was like a...
No, if I recall, I think I read this paper,
Geometry.
and I'm pretty sure like it was one of these kind of jury's still out situations.
It was. Yeah.
I mean, they're basically, I think, trying to lay the more simple claim than the than the runaway supermassive black hole, but I think it needs probably more observations to really confirm either way.
I really like that idea, but it's probably an edge-on galaxy.
It would be, the Occam's razor answer, I think.
All right. Well, Nora has the lead now with 2 points. Here we go to the next question. Which space agency has announced a mission to the asteroid belt and Mars in 2028?
JAXA, I'll take a guess.
Good guess. It's not JAXA.
ESA?
Not ESA either.
Maybe the Chinese.
Lesser known than even the Chinese.
How about India?
Oh, you're on the right track. On the right track. Hold on to that answer, Valerie. Hint, hint. It's actually the United Arab Emirates.
Oh, that was going to be my next one.
This is super cool. Their second big mission. First one was successful, and they are going to be exploring 7 previously unvisited asteroids in this mission. Should be really, really cool.
Cool.
All right, moving on. Next question. NASA scientists now have strong evidence of a polar cyclone on which planet?
I'm not going to guess India.
Not India. No.
No.
Saturn?
Good guess.
Sounds like a Jupiter thing.
Yeah.
It's we've got lots of cyclones on Jupiter. This is new to this planet, actually.
Oh.
Is it it's either Uranus or
It's Uranus.
Nice.
Yeah. It's a little white spot right of center on Uranus's north pole, by the way. Even though it's over on the right there, that's the North Pole. We now know there is a cyclone there. Some microwave radiation was used to detect that. All right, 1 point for Jan. So now it's tied, 2 points with Nora and Jan. All right, next question. Which space company recently crashed a lunar lander into the moon moments before its scheduled landing?
What's the name of the company?
Yeah,
iSpace?
not a space. iSpace, yep. Nice. But they did send back this awesome picture. I'm like, okay, you guys did good. You didn't land, but this is pretty breathtaking.
They hit like 17 of their 18 mission goals.
Yeah, the landing would have been pretty awesome, but they did not stick to landing. Apparently, the spacecraft suddenly accelerated just before landing, and then that was that. Sadly. All right, but another point for Nora. That brings her in the lead with 3 points. Next question. Astronomers recently announced that a Type 1a supernova, first observed in 2020, seems to be strange. Not only because it was observed in radio wavelengths, but because instead of having a compact companion from which it accumulated material, instead it got its material from a
helium giant, I guess.
Yeah, it was a helium giant. Not typical for this type of deal, but that's what they're saying. Very strange deal. So not your typical like degenerate pairs of two white dwarfs. One much less compact object, helium burning star. So kind of interesting. All right, it's all tied up again. 3 points.
I'm just a spectator tonight. Keep going.
All right, we got a few more questions. There is time for other folks to take the lead. Here we go. What new delineation offers exosolar planet hunting astronomers a guide for where in planetary systems life might be most likely? So we're still talking about the habitable zone here. Obviously, water is still important. There's something else, and this new delineation describes the something else that's really important for life. I give you.
Is it something to do with the amount of ultraviolet radiation?
With what?
The ultraviolet radiation from the star?
Not ultraviolet radiation. I'll give you a hint. It's a very dirty delineation.
Like the dust line?
I don't know. I mean, carbon is typically thought to be a.
Aha! Danny gets a half a point for that. So yeah, you were right, Danny. It does have to do with the prevalence of carbon in planetary systems, and there is a line for where the right accumulation of carbon exists interior to said point versus exterior. And Earth, by the way, is outside this line. It's called the soot line. And astronomers are now thinking that planets inside the soot line have a higher probability of the chance of life forming with just a larger buildup of carbon. So yeah, habitable zone, not just water, but in the soot line with carbon as well. So half point for Danny. Nicely done.
Where is Earth in that? Just out of you say it's not within the soot
Earth
line.
So Earth is just outside the soot line. Yeah.
But that's because we have so many chimney sweeps. We're the only planet with chimney sweeps, so we would be outside the soot line.
That's right. Exactly. But yeah, apparently planets with a bit more carbon. I can't remember the number that I saw earlier today. It was like a tiny fraction of carbon makes up the Earth. Way less than the percentage of water.
If Earth is outside the soot line, Earth is at like the very inside edge of the habitable zone, so it doesn't seem like there's much overlap with this then.
Yeah, and I guess that's why this one made the news. It's a different way to think about where to look for exosolar planets. Yeah, I think it actually makes the habitable zone a lot tighter.
Okay.
Yeah. It's all different because planets all migrate throughout their formation. So lines like this don't necessarily make sense. And the Earth with the habitable zone is because of the atmosphere. We can actually retain heat more. So the habitable zone can actually be a little bit wider. So again, these sorts of things, it's always good, I guess, to try and focus where you're searching. But if planets are moving around and maintaining heat in different ways, then what utility do they really have, you know?
That's a great point. Maybe they don't.
Yeah, I mean, you have to start somewhere, so it's fine, but these are not rules. They are suggested guidelines at best.
Indeed. All right, let's move on. A star exploded in a galaxy just 21 million light years away from Earth. This is like in our neighborhood, giving astronomers a rare opportunity to watch a supernova unfold in real time in exquisite detail. Which famous Messier object galaxy is this supernova occurring in?
101.
101, yeah.
Supernova galaxy. Yeah. Nice one, Jan. That brings you into the lead with 4 points. There are just 2 more questions, so it is going to be neck and neck to the finish line here between Nora and Jan. Let's see who can pull it out. Here we go. Which country launched a new generation of navigation satellites last week? This one's all you, Valerie.
India.
India! It was indeed India. All right. For the final question and the possible tie, here we go. A study published today introduces a new fast-folding algorithm that crunches over 1.5 million time series for periodic signals in roughly 30 minutes. This algorithm, which is part of the BLIPS study, is being used to look for what?
Gotta be aliens.
It's aliens! Yeah, technosignature to be precise. But yeah, this is the latest. No, this is serious. This is serious, y'all. I'm just so glad. I really hope Jill Tarter is not listening to this right now. She would be appalled. Yes, on the Astro Show, y'all. This is part of SETI's Breakthrough Listen program. And basically what they've done is they've used stuff for you, huh, Danny? They've used the idea of pulsars as the impetus to look for these rapidly repeating periodic signals, which a sufficiently advanced technology civilization could actually create, and that could be heard the other side of a galaxy, and escape all the other noise that's out there. Something as powerful as a pulsar and a periodic. So the idea is that this computer algorithm will be able to find these signals, and hopefully one of them will be artificial and not natural. And so they've tested it on some pulsars. It works, and whether they will actually find a technosignature is anyone's guess.
How is the predicted technosignature different than a pulsar?
I think the idea is that there will be some kind of anomalies with it that don't fit what we know with pulsars. There'll be some other like embedded signals. Think contact, Jodie Foster. I think that's the idea.
Okay.
Does the Earth make these sorts of signals that they're looking to detect? Like, why do they think aliens make signals like this?
This is like a much more radically advanced civilization. So we're talking like a type 2 or type 3 civilization. Our civilization doesn't even qualify as type 1 yet.
This, I assume, would be some sort of us detecting their METI, not like this is a byproduct from their society, but like this is something they'd be doing intentionally.
Exactly. Yeah, this would be an intentional signal that they would be broadcasting to basically say hello.
That seems like a bad idea. Are we going to do that at one point? If we don't
We have done it.
I feel like we should just keep to ourselves, right?
We've done it a couple times.
I guess that's true. That's true. I do not approve.
You're not alone in that.
Yeah.
No, there are a growing contingent of astronomers and other notable scientists who think broadcasting our whereabouts into the galaxy is probably not such a great idea.
I'm all for
Largely
it.
because we don't know what's out there.
No, that's how you find out.
I mean, what's the worst that can happen? It would be a super predator species and they would come and destroy us. No big deal.
I mean, all right, I won't be too cynical.
Well, actually, if you look into why did I just forget his name? The Fermi paradox. Enrico Fermi outlined all the reasons why we might not have already contacted or been contacted or come into contact with some other intelligent civilization if they are so abundant as is suggested by the Drake equation. Where are they all? Was the question that Enrico Fermi asked. And he came up with 10 really interesting lines of logic that suggest why we haven't come in contact with them. And I think the most intriguing is they just don't want us to. We're not as interesting as they are yet. And so nobody wants to be noticed by us. That seems the most plausible to me out of all of the others. But who knows? maybe SETI's going to do it with this. And all of you who just laughed about this will be sorely mistaken, but we shall see. All right. Well, Nick coming in there with that final answer means that Jan is our champion this week with 4 correct answers. Nicely done.
Thank you. Does that mean I get invited back to like be the ruling champion?
Absolutely. Yeah.
I love that Jeopardy rules. We should do Jeopardy rules.
I like that, actually. That's a great idea, Jeopardy rules. Yeah. All right. So, yeah, if you're willing to deal with the time difference again, we'll have you back. All right. Well, let's move along here. What's up, Dr. Sam, is next. A couple new planets on the eastern horizon. Not that many astronomers are early birds, but if you are out there listening and you'd like to get up early before the sun rises, Jupiter and Mercury should be visible in the early morning sky about half an hour before sunrise. And Jupiter is going to be rising higher and higher in the sky, and you'll start to be able to see Jupiter at night in the upcoming months. It'll put on a much better show during the night later on this summer. Mercury doesn't get much higher though, so just another week or so to start seeing Mercury better, and then it will get closer and closer to the horizon. Go for it, Valerie.
I saw Mercury for the first time.
Nice.
I was in the Maldives, so right near the equator, and it was there with the crescent moon, and I got to see it finally, and I got these incredible photos where when you look at the photo, there's just the moon, and then when you zoom in, there's this tiny little Mercury. It was delightful. I was up really early because of jet lag, so I took the full advantage of it to see Mercury.
Excellent. Yeah, I've seen Mercury a couple times over the years. But yeah, it's always a treat. You got to catch it just right. All right. Well, that brings us to the final segment of our show, which is our special guest segment. So Dr. Jan Eldridge, thank you again for being here. And the rest of the time is all yours. We like to start the guest spots by asking our special guests all the same question, which is, what's the one question that you wish everybody would ask you, but nobody ever does?
I don't know, because people ask me so many questions. I just love answering all the different questions. No, it's true. People just ask me all these questions, and that's actually the best bit of anything. Actually, just the questions people ask, because then you've got to try and answer these things, and I can normally at least try it. And actually, the best questions are where people ask you something, and you have to go, "We don't know," because literally that's where we're actually at the forefront of knowledge. And I love it in class when students ask me those kind of questions, because it says, you were paying attention. Which is really cool. But if there was a question that I wished people asked me, it would be, what question would you like to have answered?
Ooh,
because, you know, where do I see the next kind of thing to go to? What's the big mystery that, you know, we're trying to solve at the moment? And I think that it's one of those questions, because normally I always talk about that, but it's not one that immediately appears or is apparent to other people.
I like that. Well, let me be the first to ask you. What do you think the next big question is going to be?
I don't know, because there's so many. We're living in a very special time, and actually, what's really cool at the moment is you have JWST observing stars in our galaxy, stars at the very edge of the observable universe, and you have the LIGO, Virgo, Cagra gravitational wave observatories all coming online, because they're doing their engineering runs now, and they'll be going to their observing runs soon. And what's kind of becoming apparent is all of this is kind of related, because LVK are detecting black holes and neutron stars merging, but they're coming from stars. You know, we want in our own galaxy to find out, do these things exist in our own galaxy? Which, you know, we've got to study stars in our own galaxy because they're so close we can understand them better. But then we also need to look back at those very earliest galaxies, because they're the galaxies where the merging black holes we see today are actually still stars. And so I end up sounding a bit like a conspiracy theorist trying to talk about this, because I'm having to link all these things together. And then, you know, you mentioned the supernova in M101. that's literally happened in the last few weeks, and I'm getting so excited about it because that's actually all thesis work. And how does that link in? Because one really key question that I'd really like to know the answer of is you have a massive star, it dies, it forms this neutron star or a black hole. When it forms a neutron star, we're pretty sure it causes a supernova, which we can see. But there's evidence that when it forms a black hole, you don't. And now there's also evidence, sometimes with some neutron stars, we form them, and you don't get a supernova either. So it's this kind of thing, you know, why does everything seem to be so complicated? We had this nice simple picture, but what actually goes on when a massive star dies? That's the other problem. So there you go. That's my answer.
I love it. That's great. And that's part of the research that you do, right? You study the evolution of stars.
Yeah, which it's so simple to say that, but then the real fun we've had is not just making these models of stars, which is difficult, but it's then comparing them to the observations. You want to like observe your stars in every way, because as I kind of showed with this circular argument between all these galaxies and black holes and everything, is that a lot of studies, people say, okay, we've got these models of stars, we compare them to observations, we can learn this. But the problem is, you can sometimes say, okay, there's this other observation, and my models don't match that. And so I need to change them. But then do you still match the thing you matched before? And so it's actually, you know, when LIGO first detected the gravitational wave merger of two massive black holes, we hadn't even considered that, but we had this set of models we was able to quickly work out, do we match the observation? And we do. And it's more fun that, you know, most of the time we can say, yes, our models match what we see, but we're now starting to find places where they don't. And so, you know we're having to go back and recalculate all these models of stars and how they interact, which again is, many people do this, but we kind of do it in a way that tries to be as accurate as possible and try to do as much as possible. And it makes you very tired because you're trying to do too much. But it's the only way of trying to make progress, because we can't just do one thing anymore. You got to link everything together and be a conspiracy theorist. I should have more red tape over my room trying to link all bits of physics together.
I love it. So I was reading some stuff about your work earlier today, and you observed a strange supernova as well, right?
Yeah.
I think it was referred to as a wimpy supernova.
Yeah, that's it. It was working with Noel Richardson. He had a undergraduate student reduce some data for a star, because there was this burst of, I think it was X-rays from somewhere, so we knew there was a magnetar or some neutron star somewhere, and they looked and they found quite an ordinary looking B star, which is a star about 10,000 degrees Celsius on the surface. And so there was a neutron star in this star. You can't see the neutron star, but you know it's there. And they looked at how that bright star was moving, and it was going around and around in a circular orbit. Now, that's nice, because when you think about it, Earth's orbit around the sun is circular, so you assume most orbits should be circular. But if there's a neutron star, conventional wisdom says you must have had a supernova. And you would expect it that, you know, that would give the neutron star a kick. And so as it goes round the other star, it wouldn't go round in a circle. Sometimes it would be more like a comet. It would come in really close to the other star and then zoom out. There was no evidence of that. And so Noel said to me, found this weird star. And I went, that's weird. And we agreed it was weird. And the only answer is that this star interacted and must have been very close to the minimum mass to form a neutron star. And so all the mass went into the neutron star, which means you don't actually get any supernova and you'd still get that circular orbit. And that's really confusing, because, you know, what would that supernova have looked like? Would we have seen it? I mean, it probably happened far enough ago that before recorded human history, because we know of supernovae in the historical records of, I think there's Arabic and Chinese records back to the supernova of 1006. That's the earliest supernova we know about. So it was before that, but we probably wouldn't have seen it because it was so wimpy. But this is important for those gravitational waves, because, you know, here we have a system where actually the other star at some point is going to go supernova, and that's going to form two neutron stars in a close orbit that should spiral in. And then that's kind of exciting to actually then be able to predict what's going to happen in the future. But yeah, so that one's confusing, and we need more observations, which is always the way, because, you know, otherwise you don't really know what's going on with that system.
I mean, I remember reading in the article that there may not be a lot more observations of pairs of stars like that. It was suggested that those types of pairs or binaries are pretty rare.
Yeah, they should be. Otherwise, we wouldn't see fewer supernovae. Because if this wasn't a supernova, but it formed a neutron star, you can work out the rate of what you should see. But yeah, and it should only be a handful of them in the Milky Way. And most systems like this are in these kind of other orbits we expect, where they're eccentric with this bright B star. The B star is actually also rotating so fast because it would have taken mass from the other star that it's actually almost at breakup and it's almost flying apart, which also makes it interesting. So there's many of these type of systems, but very few with this rare circular orbit.
Gotcha. Very cool. You mentioned a few minutes ago that there are some examples of black holes forming without supernovae occurring. Say a bit more about that. That's really cool.
Yeah, well, there's one, maybe two, right? So how do you find a supernova? It's really easy because, as you showed in that image, right, you get this really bright. Suddenly there wasn't anything, and then there's a star, because like a supernova will output as much light in a few months as the sun outputs in 10 billion years. That's the kind of energy we're talking about, and that's why they can outshine their own galaxy. But to find stars that don't go supernovae, you basically got to follow billions and billions of stars and find the one that disappears, which is a lot more. And the problem is stars vary anyway, because do you remember a few years ago, everyone got really excited that Betelgeuse got fainter. Yeah, and then it got brighter again, and now I think it's 115 times its normal brightness or something. So how do you do this? And there is one case of one star in the nearby Fireworks galaxy, which I think is NGC 6946, which has had 10 supernovae in the last year. Yeah, but I'd have to look it up. But it's called the Fireworks galaxy because it's had 10 supernova in 100 years.
Yeah.
So things keep off going off. But in the same galaxy, they saw one red supergiant like Betelgeuse suddenly disappear. And it's the best candidate we have. But otherwise, while we can see that one star, and there's a few other examples of these things just disappearing, we have to follow them to see if they reappear in 100 years or so. But when we make computer models of stars up until the very close end of their lives, we see that it's actually stars above about 20 times the mass of the sun. They form black holes, and they may not form supernovae. But it's difficult because we're trying to model something that takes a few seconds of real time. But when you're modeling it in a computer, it's difficult because you have so much physics to put in, and it takes actual years of CPU time to model this few seconds of what goes on. And we can't actually model it far enough to see what happens over days, weeks, and hours. But our guesses are that it does form this black hole, and everything just goes into the black hole rather than exploding. So knowing if that's true is like the real question I really want to know about. And we'll know about it, and the gravitational wave observations will tell us something about that, because those black holes must have been formed by stars. Okay, let me correct that. Most of those black holes were probably formed by stars. There's always cases where you can get other things happening, otherwise people will tell me off. So that they will tell us, and that's what's exciting about this fourth observing run of LVK, is we're going to get hundreds of black holes, and now we've got to get that population. We may actually be able to say something much more about how these black holes are formed.
Very cool. I am excited about that. That's going to be very, very cool. So you mentioned computer programming, and you wrote a program called BPass that you use in your research, right?
Yeah. So this is something that grew when I was back doing my PhD, all the way back at the University of Cambridge in 2001 to 2004. I was working with the Cambridge Stars group, where they had this code that was actually written in the 70s. No, actually, sorry, it was written in the late 60s,
Wow.
but was published in the 70s. So the code is written in Fortran 77, which is the best programming language in the world, because all astronomy codes are written in Fortran 77, right?
That's a joke, by the way, folks. Those of you listening.
I'm serious. I will defend
Fortran.
Fortran.
Fortran components. So
There's a lot of Fortran.
there's a lot
still.
of Fortran.
Yeah. And so at its heart, BPass is still that code written by Peter Eggleton all those years ago. But of course, we've modified it. We put in new physics. And I put in a new way of studying the binary stars, because when I was doing my thesis, it was clear that if you try and model supernovae, they're not all from single stars. Most of them come from binary stars. This is where you have two stars orbiting around each other and they can get in each other's way. So I was just looking at those supernovae, and then my friend, who was doing the PhD at the same time, Elizabeth Stanway, said to me, like, apparently galaxies are made of stars. And I didn't know this. And she said, there are these galaxies at high redshift. Back then, this was a redshift of 3, so not actually that high redshift today. But the spectrum of these galaxies couldn't be fit by standard single-star models. And so that led us down this path of making these models, not just comparing them to supernovae, but predicting what entire galaxies would look like. And that was great, because then you've got the same model set being constrained by 2 observations. And we was able to show that these high redshift galaxies have binary stars in them, and also really rapidly rotating stars like the one in that wimpy supernova system we talked about, because that makes their spectra look very subtly different, and you can pick that up. And so you had this bit that made the stellar models, then predicted what they look like by using other people's work. And so actually it's really a thing where it brings together all these things that people have done together. But we've had to build upon that because of gravitational waves. So we've now got these other bits of code. So it's like not just one code, it's like it's getting a bit more unwieldy, but there's lots of different things we can do with it. And so now we can predict the gravitational wave observations, and we can predict supernovae. We've blown up some of our models to see what they look like when you actually blow stars up to compare them to observations. And it's a huge team of people. Like we have now maybe 20 people, including postdocs and students, that have been working on this over all the years. And actually, it's the only way you can do this. I used to be able to do all the work, but now I need this team of students and postdocs to be able to do it. And it's so much fun working with such a large team who are all really keen and want to know the same answers I do. So, BPAS is not also just a code, it's actually a group of people. And I think that's really key.
Nice. That's fantastic. Well, let's shift gears a little bit. I'd love to hear about your path that led you to become a professional astronomer, and how that all happened.
Yeah. So that's interesting, because whenever I give a talk or like a lecture and introduce myself, if I have time, sometimes if you've got 15 minutes, you skip over this bit. But I always talk about, why do I do astronomy? And there are 2 slides I show. The first one is Doctor Who. So, I grew up in the 80s, and the 7th Doctor, Sylvester McCoy, was on the screen. And, that's kind of, and actually being an astronomer and a professor is kind of like by being Doctor Who, because you get to explore the universe, work out how it works. You get to take people with you, young and old, to show them the wonders of the universe. And, when you're an academic, you also do try and make the world a better place. You try and make that academic environment better so that everyone can come to university and succeed in their studies, which is, I think, what Doctor Who does. And it's not just Doctor Who, it's all science fiction, so I like Star Wars, I like Star Trek. I like all the novels of people like Arthur C. Clarke, Isaac Asimov, Ursula Le Guin. And it's just, being an astronomer is as close as you can get to all those science fiction shows. And so was always the impetus and always in the background as I went through school and university. I'm the first in my family to go to university. It wasn't until I was at secondary school, about 13 or 14, when I talked to a careers advisor and said, well, I watched these Royal Institution Christmas lectures about physics, and I thought maybe I should be a physicist. And that was the first time somebody sat me down and explained, okay, you need to do an undergraduate degree, then you do your PhD, then you do some postdocs, then you try and get a lectureship, and then you work your way up the ladder. And almost from that moment onwards, that set my path. And it's not always been successful all the way through, because, so as I was going through, I took 2 years to get into the University of Cambridge. I didn't get in the first year I applied, so I reapplied. I took a year out, working for a company called CompuServe, which in America, you may remember. When CompuServe came over to the UK, I was there on their technical help desk. But I reapplied to Cambridge and got in. And then I studied there for 4 years, applied to do a PhD there at the Institute of Astronomy, and got to do a PhD again. But I was on the reserve list and quite far down. So thank you, everyone who didn't accept the place, so I could go there. And that started me on this path to where I am today with BPAS. And, I applied for different postdocs, went to Paris, which Paris is a wonderful city to visit, but living there for a year is not so great. Then I went to Belfast in Northern Ireland, which I absolutely loved, and then got to go back to Cambridge. And then moved to New Zealand in 2011. Now, one of the subjects here is that over all that time, I did academia and my studies on easy mode, because back then I was thought I was a man. And I thought you actually had to be a man to be successful in physics. And that's just because of the upbringing I had and as what I was exposed to in the 80s and 90s. But I always knew that I was more complex than that. And so that's when I moved to New Zealand, though. And the university set up an LGBTI or Rainbow Staff Student Group. I was able to meet a group of students who had set up this thing called Trans on Campus, which had been able to try and make changes at the university. And so the university now, for example, funds name changes for students to help their safety, but also to say, look, we recognize who you are and want to help you on that path. And many other minor things that we could go on to. And I now know more about toilets and toilet legislation than you could possibly want to know. Building codes are great about toilets. They're just the most interesting read. We thought astronomy papers are interesting to read. But what that also gave me was the knowledge to be able to understand myself. And one of the great things about astronomy, right? We all think the universe is so complex and wonderful, right? Because we go and look at the stars and literally we get mesmerized. And one thing that commonly happens is when you explain to people about space, they go, wow, it's just so amazing. It's difficult to get my head around. Turns out people are complicated too. And gender, sex, and all these things are immensely complicated. We think we're simple because we all have a gender and a sex and these kind of things. But as I understood this and actually have up to my understanding, it's like, no, it's really complicated. And actually that was able to give me the chance to try exploring who I was. And so I'm now going in the more tricky mode of just being myself. And it's interesting, even though I have other things to worry about now, transitioned into being a woman. But the problem is I'm so much happier. So I'm not worrying about it so much. So even though I've got extra things that I'm having to worry about, I can actually get so much more work done. And one of the only reasons BPAS is so successful is because when I stopped fighting myself around about 2015, I was able to achieve so much more and work with such a large team. And actually, it's huge because you're suddenly got this entire burden left off for yourself that you can actually contribute and make changes across all the ways. And so that's, and it's crazy because now people just email me about different results and things because they want advice on doing science. And it's, again, it sounds like a conspiracy theory, but it always all linked that suddenly you become happy with who you are. And suddenly you can achieve at work, and then you can achieve success. So yeah, it's kind of exciting to look back, and I think I've done that entire 20-year arc in like 5 minutes. But
that's a great story.
It's been interesting. It's an interesting thing, yeah.
That's a great story. Yeah, thank you so much for sharing that with us.
Yeah, you're welcome.
So, I mean, if you don't mind me asking, how has that been in the astronomical community? Do you feel like there's a growing network of support for that? Was it really difficult at the beginning and getting easier? Or?
Yeah, I mean, so it's interesting because New Zealand and Australia are actually quite isolated from the world because we're right down the bottom. And in fact, if you look at some maps, you can sometimes New Zealand is left off. They put on Australia and forget to put on New Zealand. Yeah, no, it's on the one behind Valerie. Yeah. Just checking. And so it's a completely different world. And actually, if I was anywhere else in the world, it would be much tough, especially when you look around the world with the legislation that's coming in some countries. In the US and the UK, I would probably not feel safe to be myself right now. But in New Zealand and Australia, and also because there was the Astronomical Society of Australia, they were doing a huge amount of work in this space as well. And it was just at a time when I was going between Australia and New Zealand for their meetings and was able to make them stand up and give some talks over there about, the rainbow community. I had a huge amount of support. And actually, what's interesting is I know that there's probably been support that I don't know about, where people have had conversations with other people behind the scenes to educate them before they actually go and meet me. And so I don't encounter less support. Even in America, though, still got a huge amount of support from astronomers over there. And where was I going with this? But I know there's elements of people that, think I'm mentally ill. So I did once organize a conference, and one night somebody posted on the Facebook group for the conference that I was organizing that trans people are mentally ill. And that's kind of nasty. But and I know that there are the rare number of people who are anti-trans in astronomy, and I can't do anything about them. All I'm trying to do is try and do really good science, making the best science I can. So they have to say, okay, we actually need to use that, and start. They can't just dismiss me because they go, that person is a crazy person, we can't use any of their work. But it's that part's still difficult, and especially when you end up being invited by someone to be a co-author on a paper, and you see that person and you have to think, do I actually go on that paper or do I not? And it's more powerful to win the battle and say, no, I'm going to go on that paper, and then see the games that author plays with the author list. That's kind of fun. And I know that means I've won the battle because they're already thinking about it.
Yeah, well, sorry that those issues are still so prevalent today, but really appreciate all the work that you've done and trying to make that a safer place for everybody.
Yeah, well, I can only just be me. That's the end of it. And it's interesting, some people think that every person in the rainbow community is an activist. I would love not to have to do this stuff. But one thing I learned when growing up with my parents is, if you see a job that needs to be done, you do it. And I've got the privilege because, as I said, I did it on easy mode. I didn't transition till once I had a permanent position and I had a certain level of kudos, of whatever you want to say, or profile in the community, that I could take this change and then use that to make those changes. So, but thank you.
Yeah, thank you. Well, we've got just a few minutes left. I always like to give our special guests the last word, and so if you have any words of wisdom or special insights that you haven't already shared with new budding astronomers or anybody, we're all yours.
I can't think of any.
That's all right.
No. I mean, one question sometimes people ask me about anything to do with this is, what would be your advice to other trans or rainbow people that are in the closet? Should they be themselves? And the one thing I would always say is actually the one thing that must take priority is your own safety. And you can be yourself, but primarily think about your own safety more than anything else, because you're more precious we're all very precious. And so we've got to make sure we take care of ourselves before we start trying to take steps to try and be ourselves. But so just take care of yourselves, I think, is always a really good last line to actually say, even though that's maybe a bit flat after everything I just said.
No, I think it's fantastic. And I think that's certainly pertinent to folks in the LGBT community, but it's also pertinent to all of us who work really hard to do what we love to do. We all have to take care of ourselves as well. So I think that is fantastic advice.
Thank you.
Well, I've taken up a lot of the talking and question time as well. The co-stars, do you have any questions or comments or anything else you'd like to add before we wrap things up?
I do. So first of all, Jan, your story is so profound, and the message that you communicate to all of us is just very, very profound. And I'm curious what is next for you, and what are you most looking forward to moving forward?
I don't know. So I'm giving next Wednesday, I'm giving my inaugural professorial lecture in Auckland. And I'm ending it with I don't know what's next, right? So I've just been promoted to professor, which is great, which shows you that I've got this research career and everything else I've been doing. And, I've transitioned to my point where I am now. And I'm still, of course, transitioning because it's a lifelong process. But in both those journeys, I don't know what's next. So I'm currently head of department. I really like leadership. Leading a department is amazing. You get to encourage other people and empower them to actually find out real new discoveries. Do I want to do more leadership? Do I want to do more research? Do I want to do more other things? And come back in about a decade and I'll let you know how it went. But it's a really exciting time because I don't know what I want to do next, and that's exciting. And one of the problem is because there's some people I can look at and see elements of who I want to be, but there's no one person I want to be, and so it's actually very difficult to answer that question. But thank you, Danielle.
Yeah. Thank you.
Well, I don't know if there's a better place to leave it than that. Unless any other the co-stars have something more profound to say, maybe that's a great place to, to wrap things up. Oh, Val, you're going to go for it. All right.
I was just going to say, I'll see y'all in a decade. I look forward to hearing the answer to this question.
Yeah, likewise. Well, Jan,
I don't know if I can deal with that pressure.
No pressure.
we will have you back sooner than a decade. But in a decade, it's a date if you're still interested in coming back on the Astro Show. If we're still around by then, we'll see. Wyoming Stargazing is coming up on our 10th year anniversary this July. Actually, we're going to be 10 years old. So a decade seems like a long time. But yeah, who knows what Wyoming Stargazing will be doing in another 10 years. Also very much up in the air. Jan, thank you again for being here today. It has been an absolute pleasure chatting with you. We really appreciate all your time and all the amazing work that you're doing in so many areas.
Thank you. And thank you for having me. It's great. It's really a fun show. Yeah,
it's our pleasure. And Maggie, our operations director, is going to reach out to you with a thank you gift. So again, thanks so much. And thanks to all the co-stars, as always. We would not have the Astro Show without all of you. So thank you all for being here and sharing your time and expertise. It is greatly appreciated. Thanks to all the folks behind the scene. Maggie, Wyoming Stargazing Board of Directors, our program coordinator, Vyamika, and all of you watching live and those of you who watch us recording. We appreciate you tuning in, and we hope to see you again next time in a couple weeks. Until then, be well, and don't forget to look up. We'll see you next time. Bye.